in section 2, we're gonna see and we're gonna learn how we can still perform the same transformation of a one-dimensional object, which is a line, on the plane. At first, in the first section we learned about transforming a line. This case is pink line on a line. But in the second section, we have a plane now. We are living in the 2 dimension, but we transform a line. What does it mean to transform a line on the plane? And we will find out that this is actually the definition of vector. Of course, we can actually replace that by vector, but I use it this way to draw the connection between these 3 topics together. So we can start learning about vectors. So the motivation is, let's say we have this image. We have the line on the left, which is a W, this blue line, and we want to transform it into another line segment, in this case the green line, V. Have you learned this before? Of course not, because I changed the class structure. Yeah, we haven't learned this one. But yeah, that's the idea. So we have a line, and we want to transform it to another line somehow. How can we achieve that? And you see that in a moment. But I found this meme somewhere. I don't know what's the context. You just got vector, so it's about vector. So first thing I noticed that I draw a line with an arrow. There's an extra vector. And actually, if you go back, maybe a better one is to also think of this segment as a line with an arrow. So you have a line. Maybe I should draw it this way. Previously, you can think of what we just did as a line starting at 0, and it ends at some point. Let's say A, and it has an arrow. But in 1 dimension, right? It doesn't matter much like what the values A is. There are not much we can do with it anyway. Yeah. But in 2 dimension, and once we put that line or that arrow onto the plane, there are more things we can achieve, which we're gonna see in a moment. But first, let's define that thing, the thing that we just drew up here, like this blue arrow and this green arrow, as a new object called a vector. There was a clip which I don't think, I don't have it here. But if you take a look at my other lecture, you can see I talk about a vector for a bit. Like interestingly, like you may hear this word everywhere, especially if you use like image editing software. Like there's an SVG format, .svg, which stands for, I forgot what S is, but V is the vectorized. G is graphic. Actually, now that I'm at it, let me Google it. Yeah, scalable vectorized graphic. Oh yeah, that vector, the V, that is actually the same definition as the vector that we are going to study. And also, like there was a clip of Tribu One Brown, a famous YouTuber in the math area, that actually this vector has 3 different meanings depending on who you are. If you are a physicist, and this is actually what you might heard about this vector in the first place, which is in physics, which they think about a vector as whatever that has 2 properties, that has the length and has direction. That one. If you can describe how long is it and where is it going, where is it pointing at, then you get yourself a vector, which is sort of abstract. But again, there's that might be the definition that most people are familiar with. If you're a mathematician, vector is kind of wired, and I don't recommend you go into of mathematicians to do much detail about that. But yeah, we think about vector as some abstract number that you can, and we can touch this a little bit. There's some abstract number that you can add together, you can multiply, you can do some stuff about it. And this vector needs to have some kind of properties. It has to be linear, it has to be blah 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 blah. And again, we're gonna write some of that, because we want to express what we are doing. But when you actually compute, we are actually in the term of the computer scientist. If you are computer scientist, or data science or other stuff, you are actually thinking about a vector as just a number, as several numbers stacked together in a column. In this case, we have this v1 and v2 as two numbers. Oh, let's just put it 3 and minus 2. Stack numbers together in a vertical fashion, as you can see on the left here. And once we have that, then each number can represent something, like whatever you want to. And again, we can still perform some operations, add, multiply, do all the stuff. But they are now just numbers. And in practice, it is useful to go back and forth between mathematics and computer scientist view of vector. Okay, they are numbers. You can add numbers together and multiply numbers together. But if you ask what does it mean when you add two numbers together, or to add two actors together, then you have to go back to ask your mathematician's friends and say, oh yeah, adding them means you put them next to each other or something. And so yeah, that's 3 different vectors for you. Sometimes you want that, sometimes you want to be math, sometimes you just want numbers. But we are going to focus on these numbers, how to write or manipulate these numbers and what they mean in terms of math. And yeah, on the left there are 2 definitions here. The first, we define pretty abstractly as a line segment with an arrowhead at one end. Abstractly. Oh, I should also add that it is in any dimension. You can make it a 2-dimensional vector if you draw it on paper. You can make it a 3-dimensional vector if you draw it in a 3-dimensional world. As a stick of wood pointing somewhere. But yeah, abstractly it is that. And it has an initial point where it begins and a terminal point where it ends. So it's kind of like have 2 points with an arrow. The arrow is on the terminal point, the ending point. Yeah, abstractly, that's a vector. But mathematically or computer scientistly, that's a word, I'm not sure. We express them as the column vector. So on the left we have a name, again, just like the function, you give something a name and some symbol. Like this vector has a name v, and that's a name. And we put an arrow on top of it to indicate that, yeah, it is a vector. You should treat it as a vector and do stuff as a vector. On screen or in a book, you see this arrow, but when you write, usually you only have the top left. The line above, not below. Because you don't want to lift your hand too much if you write a lot. And so yeah, when you write, usually. Also, when I write on screen, you will see that, there's only one line. But yeah, nevertheless, that's a vector. And I should also say that this is a 2-dimensional vector. Because there are 2 numbers. There are only 2 numbers here. One on top and one at the bottom. Of course, you can make 3, 4, 5, 6-dimensional vectors. That's going to be useful at some point. But not now. For now, all we need to know is how we can define a 2-dimensional vector. And what can we do with it? So, that's a vector, like kind of a vague number system. But there's a more formal definition. So once you have a plane, then we should take advantage of the plane notation and think of them as points. So there are two ways to draw a vector. First, like abstractly, you can have a point P, you can have a point Q. Again, just some names. And if you draw a vector from P to Q, like this orange vector, the result is a PQ vector. So that's how you denote the vector from drawing or connecting these 2 points together. So yeah, the arrow on top indicates that it's not a line, but it has a direction. It is a directed line segment. Oh, that's a vector. We have any 2 points, just give it a name. But once you have if you express this point as a point on a plane, like let's say that this point P is AB, this point PQ has a coordinate C and D. And once you give them coordinate, then we can actually compute that point. And I think it means something. But yeah, at first, usually or almost always, we express a vector as a line starting from the origin on the point or the coordinate 0, 0. To simplify things up, if you start at 0, 0 and you go to a point AB, then you're gonna form a vector. Oh, I should change the color to be consistent with what we have above. 0, 0 to a point AB. Let's say that's a point. Then the result, and this vector is the AB vector. Notice 2 things here. First, the point or the coordinate is written in terms of coordinate. It has a parenthesis and a comma to separate these 2 values. While a vector is a column vector. In this case, A is on top, B is in the bottom. And second, this yellow coordinate is just a point. It's just a single point. But the vector represents the whole line. That, okay, if you move from the origin to this point, then that whole movement is represented by this vector, AB. That's how you define a vector. And oh, by the way, sometimes if you don't want to stack them up on top, sometimes you can write it in line on the same line, but the parentheses need to be the sharp one, to distinguish this vector from a point. They have the same numbers A and B. So, a point has no sharp end, so it's curved. Maybe that helps distinguish between these 2 numbers. And lastly, this is not in slide, but I should also add, if instead you are given initial point of AB and the terminal point CD. So now let's say that you move to any other points on the plane. See, oh yeah, there's a formula there. Sometimes they use x1, y1, x2, y2, but yeah, let's use AB and CD. So let's say that's the initial point, AB, and if you go to the terminal point, CD, the vector between these 2 points, starting from AB and end at CD, right, can be actually this should be like that theorem. Now this vector is a vector C minus A, D minus B. So you take a difference between these 2 values, which at this point it might feel confusing a little bit. But if you actually go back to the definition, then you should be able to see why we define this way. Because remember that the original vector, right? Erase them. In the original vector, we start from 0, 0 to AB. Now I remove everything. This is saying that, okay, we want to move A steps to the right, and we move B steps up. And so this involves two different movements. And this vector AB means we move A steps to the right, B steps up to a new point, whatever it is. But since in the original picture we start at 0, 0, then if you start at 0 and move A steps, you end up with the coordinate of x equals to A, from 0 to A. And likewise, once you move up B steps, then you move from 0 to B. Okay, so that's how we get to this number. And then, likewise, we want to ask how many steps do we move to the right? How many steps we move up or left? The number, the pictures can be flipped or whatever. But to simplify things, suppose that AB is on the bottom left, CD is on the top right. Right, how many steps do we move to the right? Then we start at A and we end at C. Because CD means the x coordinate is C. So the distance here is of course C minus A. If you measure the length or the distance between these two, it's not distance, sorry. If you start at A and go to C, you get this number. And likewise, right, this B coordinate is here, D is there. So if you move up, right, from y equals to B to y equals to D, and then the distance of the number is D minus B. So that means this vector, it can be represented as C minus A. Right, so you start at A. You want to move to C, so you have to move in the horizontal direction by C minus A point. And likewise, you have to move up or down, or in the vertical direction by D minus B point. That's the vector. Make it orange. Yeah, orange. Which is okay sometimes, but usually we almost always start from 0, but sometimes you're gonna move it around. So if you are given points, you can create a vector of that point. And yeah, that's an image here. And then notice that these vectors, it doesn't have a name. V and vector W are actually the same. In the sense that if you compute, what is it, the vector B? Vector V, this orange one. Okay, you move how many steps to the right? 5. How many steps up? 2. So this orange vector is 5, 2. What about W? The blue vector on top of here. You start at 2, you move to 7. That means you move 5 steps to the right. You start at y equals to 0 and you end at y equals to 2. That means you move 2 steps up. And so they are the same. So once we define vector as a difference between 2 points, right, then it doesn't matter where you start. And you can have multiple copies of the same vectors on the plane. So that's another concept about a vector. Let's look at some quick examples and some computations. Yeah, so find the position vector. Oh yeah, it has a name called the position vector. So there are 2 vectors here. The first one, if you draw an image, you get 2 points. The first point is at 2, 3. Let's be 2, 3. It ends at point 6, 4. The question is, what is that position vector? It's as simple as, subtracting numbers. You start at 2, you end at 6, so you go 6 minus 2 steps to the right. You start at y equals to 3 and you end at y equals to 4. So you go 4 minus 3 step up. Yeah, the result is simply 4 and 1. For this orange vector, that can be represented as the 4, 1 vector. And likewise for B, we have a different vector. In this case, it's -1 and 2, which is something like that. This P is 1, 2. Q is 3, -4. 1, 2, 3, 3, 4, something like that. Oops. My head is in the way. That's Q, 3, -4. And you can see from the graph that, oh, we are going down. The y value of the end of the terminal point is lower than the y value of the original point. But nevertheless, you can compute the vectors by simply subtracting. So subtract the x coordinate. And if you start at -1 and you go to 3, then the amount of time or this distance you need to walk to is 3 minus -1. And likewise, if you start at 2 and you go to -4, then you have to walk -4 minus 2 steps up. If you do the math, then the result should be 3 minus -1, so it's 3 plus 1 of 4. And then we have -4 plus 2, which is -2. So that's the result. Okay, so go from P to Q, you have to walk 4 steps to the right and -2 steps up. And -2 steps up means 2 steps down. So that's the answer. Maybe I should not make the both be equals to 4. Wait, that's how you can compute a vector given 2 points. And then, yeah, maybe I should also visit that first. Because again, like the definition of a vector, like you ask how many steps you walk to the right and then how many steps up. And when I said it, right, to the right and up, to the right and up, it's like, hand waving. What is right, what is up? So it would be better if you just define what it means to move to the right and what it means to move up. Moving to the right can be represented by this vector. So again, if you go back to the plan, moving 1 step right, it means you start at 0, the origin, and then you move to this point. And that's what we mean by 1 step to the right. And that indeed can be represented as a vector I, which is a vector 1, 0. Oh, and by the way, the way I use I in the lecture note is to make it a bold face. You can see it is slightly thicker than the normal text. Right, but when I write it, I cannot write it as a bold face because that looks weird, right? So that's why when I write it by hand, I put the vector notation instead. But they mean the same thing. Actually, maybe I should also use that notation instead. But anyway, now we have a formal definition of what it means to move 1 step to the right. And likewise, moving 1 step up is this vector j. And that can be represented by this up vector. Also, maybe it looks weird that you move up, but the number 1 is down. Why? Oh, because the up and down position doesn't reflect the up and down position in the actual plane. It's just a way to write 2 numbers in a nice way. But yeah, this vector j here is a vector 0, 1. So you don't move in the x direction, but you move 1 step in the y direction, in the positive y direction. So we have a better definition of what it means to be right, left, or up and down. And the interesting thing about this one, this is the math part begins. If you don't use this, if you are not too mathy, just use this for computation. Then you don't even need this. But just in case, sometimes we express v as v1 times vector I plus v2 times vector j. Okay, so but this is actually like describing the movement in inwards. So you move v1 steps to the right, and then that's the addition plus. You move v2 steps up. So in one way, it's more intuitive than this number. It's like reading from left to right. On another way, it's maybe too abstract. But yeah, just a fun fact, I guess, in case you see that somewhere else in your life. So now we have a vector. For now, just a line that floats somewhere on the plane. We don't know yet how to make use of that, but we're gonna know that soon. And soon means now. So once we define anything in math, anything new in math, the first thing we should ask is, what can we do with it? Can we add? Can we multiply? Can we divide? Can we subtract? Can we flip? Can we break it apart? Can we, combine things? Lots of things you can think of. But the basic ones that we use in this class, and actually like in anywhere you see vectors, these are what you're gonna see. So we have this new notation, and there are two ways there are two basic ways you can operate on vectors. First, we have the scalar multiplication, which is you multiply a vector by a constant. We'll see in a moment that seems familiar. So the way we write a number outside the vector, and then we just follow it by a vector, which looks weird, but maybe sometimes you might see the multiplication symbol, but most of the time you don't. This is a notation, or actually it's k times v. I should also add that, like k times a vector. That is a name. You can write it as k times a vector. If you expand the vector itself up, then you compute it by multiply k to both of the numbers on above and below. And we will see in a moment why we have to multiply them on both to make sense. So that's a scalar multiplication. And then we have an addition. And again, that sounds familiar. It's like something we just learned in part 1, but if you have two vectors, let's say v and u, when you add them up, then you simply add the numbers up. Add the top to the top, add the bottom to the bottom, and you get a new vector. The question is, the first thing is, it seems intuitive. If you do things, you should do things this way, right? But then the next question is, what are the results? And why do we have to care about multiplication? Why do we have to care about addition? Because this is actually what we just did in the section 1. Right? Multiplying is actually the dilation, if you can recall that word, or scaling, right? Like scaling. And you scale a vector by a number, and this operation is kind of intuitive. So let's say you have this vector v, and I can show you from this, because we are using a drawing app, and if you click on the corner and move it, then you can see what is going on here. Scaling. Whoop, 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 whoop. And that's what we are doing here. Like multiplying a vector by a number gives you a new vector. Oh, not that. Let's say this vector. Where is k? It's a multiplier. Oh, I think it's called like a scale factor. It tells you how much the vector gets scale. Right, and the reason why we have to do this on both top and bottom, because if you have something like if you have this green v vector, if you only scale by in the x direction, the result would look like that. Like where you keep the same y coordinate, the same height, but only scale in one direction, and that looks weird. That doesn't look natural, like compared to what we just did. by scaling it up and down. And so scaling needs to be done on each component, on both the y and the x coordinate. So that's the result of a scalar multiplication. The way we did it is fine, how we should interpret it. And yeah, it depends on k. If oops. And likewise, we can say things about k. We can make some observation about k. If k is greater than 1, it means the scale is greater than 1. And once you have that, then you should get a vector that is longer. Maybe a bit longer, maybe much longer, but in any cases, what they have is that they still share the same direction. Just like, when you scale anything, you still keep the same direction. Or like, if you drive a car, one car only drives for like 10 kilometers per hour, versus one that drives 120 kilometers per hour. The other one is gonna go faster, but the first one, the smaller one, still goes in the same direction, just slower. If you get there at some point. If k is between 1 and 0, this is actually what we would expect as a shrinking. The vector gets smaller, which makes sense, right? If you multiply everything by 1/2, that's the same as decreasing the size by half. But that's a shrink. And again, when you shrink by some factor, it still has the same direction. On the other hand, if k is less than -1, if this number is a negative number, we kind of have we actually have the two. You can think of those numbers as in two steps. Right, first we have a scaling by a positive number. Then this negative part is actually. Oh, sorry. Let me do this way then. This negative part means you go in the opposite direction, and then you scale it by a number. Actually, yeah, this is a minus a vector. You flip it back, and then you multiply it. You scale it. So this will be the result from multiplying a vector by a negative and high number. And lastly, if you have a number between -1 and 0, you have a vector, you flip it, you reverse it to the opposite direction, and you shrink it. Okay, so that would be the multiple ways to multiply a vector by a scalar, which is, again, think of it as a moving things around this way. It is a scaling. So that's the scaling out of the way. Now we have the addition. The addition, it depends on where you study. If you study physics, addition is used a lot. If you study computer science, then it used sometimes, but it doesn't have a nice property, so sometimes you just don't use it at all and just stick with scalar. This is addition. Right, so if you have two numbers, you add them together. Even if I hide that from you, the best guess or the first guess that should come to your mind is that oh yeah, just add top together and bottom together. And this is one advantage of expressing a vector in this way, because you can see top and bottom separately. Versus if we happen to write in this way, in the horizontal way, then you have to kind of like jump across that to say, oh, it's C1 plus U1, and then it's V2 plus U2, which is also true. It's the same expression, but it's written in two different ways. So if you have a vertical one, then yeah, this should be in the natural one. A better question is what it does. Why do we add vectors together? Okay, so And this is the place where physics point of view is helpful. So imagine that you have an object. Let's say there's a ball, or maybe we do it this way. Suppose you have a ball there, right? And there's finger. I can draw finger. Say that's a finger. Someone, yeah, something like that. They should point a finger to the object and push it in some direction and then stop. So this person would push this object to this point. Right, on the other hand, right, let's say that's another person. Let's say a fish or something. I push this object to another point and stop. Or let's say another finger. Right, the question is, like the physics question is, what would happen if these two fingers push this object at the same time? And they still accomplish the same movement. You try to push it through in one direction. Now, what would happen? do you expect to see this kind of movement where it stops here? Like the first person push all the way, and then this person move their finger there and then push it this way? No, right? It's not gonna be natural. If they both push the same object together, then what you would expect is you would expect it to move in kind of like the diagonal direction. And I know that the word diagonal doesn't make sense here because everything is diagonal. But yeah, something like that. Like it would still move in a straight line, but in a line that is totally different from these two. And this is the way physics and everyone think about adding two vectors together. If you have two forces combined, the result should push the object in the new path with these two forces combined. And the next question is, this is the way it is defined to make sense. The next question is, how do we find what is this orange vector? What is this combination is? So let's say that's vector v, that's vector w. Then intuitively or naturally, like this should be the sum of the two vectors. But how do we define that? Then yeah, we define it interestingly. We define it as if we push them one at a time. As if we push the object using the blue finger first, like this V first. No, that shouldn't be pink. And then, like once it stops, then we start pushing using the other finger, W. So that's how you add two vectors together and get the result. And also likewise, like if you think about it, like you may ask, why do we have to push using the blue finger first? Can you push using the pink finger first? The answer is yes. And indeed, if you do it that way, you're still gonna get the same result. And here we use a math fact that this is parallelogram, and so they meet at the same point. So yeah, it doesn't matter which one you do first, the result is the same, which gives you some kind of immediate property that you can switch the order of addition for vectors. So you switch the order of addition for numbers. Nice, for vectors. Yeah, that's how you would define addition. That's how you would visualize, or attempt to compute the addition. But eventually, if you ask, okay, how do we do that then? Then let me share that a little bit because it should be easier to see this way if I write this way. So if we have a vector v in this case and u, then the result is this vector which is u or v plus u, which is I think I used a u. My bad. Just stick with the U. And yeah, the W and U are close. So the question is, how do we compute for V plus U? So for V, like this vector V means you move to the right by V1 step, or let's say V is V1, V2. And also vector U is U1, U2. So let's move to the right a little bit. So V1, V2, this implies that we start from any point, right? And this V1 tells us to move to the right by V1 step and move up by V2 step. And likewise, once we get to this point, and then we move using the vector vector U, this pink one, this means we move to the right by U1 steps and move up by U2 steps. And the result, you can fill in the blank. This is kind of like a nice area. That, if you want to move using the orange vector, move to the end all at once, you wouldn't have to move to the right by, you name it, you have to move to the right by V1 plus V1 plus U1, the sum of the horizontal coordinate or of the x coordinate. And likewise, we have to move up by V2 plus U2. That's the reason why we define the addition this way. So that's the vector addition, and how we should define it, what it represents, and how do we actually compute it. Oh, and one last thing, like adding vector scatter is actually what we call last time as the translation. Remember that translation means you move from one point to another. And here, since there are two dimensions, we move in both directions. And that movement is actually can be described using a single vector. And also note that this might feel weird, that sometimes, if you want to move a point by a vector to get to a new point, is it actually easier to think of this point, like to first transform this point to a vector first, and then use the addition of two vectors together? So for instance, let's say this is a point AB. If you translate by the vector CD, it is easier to first transform this point and think of this point as a vector AB, and then we add two vectors together to get a new vector, which is A plus C, and then B plus D. And then finally, get it back to a point, the point A plus C and point B plus D. So there is some kind of like a dynamic change between point and vector back to point. And so later on, maybe not now, but later on, it is useful to think of points in terms of vectors instead, and only get back to points when you need to. If everything is vector, then these kind of operations are simpler to achieve. Alright, so we have a vector operations, these two operations. Right, there are actually properties, which I think I should skip that because, again, otherwise it's gonna take too long. But something, some notation. Like there's a vector 0. Just like you have a number 0 that has the property that you can add 0 to anything and get back to the number itself. Likewise, we have the 0 for the vector as well. But since it is a vector, then we need to put an arrow on top of that. Wait, that's a 0. If you add anything by a 0, then it's like you push nothing, you do nothing. The result doesn't change. And also there's this notion or notation. It is very useful because remember that if you multiply a vector by -1, this is the same as dilation. You flip it, and in this particular example, it is actually called a reflection. So you go from a line to another line that goes in the reverse direction. You can think of v times -1 as -v, and vice versa. And if you go back and forth, that's gonna help you in determining stuff. Like for instance, if you think we kind of teach you only the way to add two vectors together, but of course you are free to subtract that. Subtraction gonna take some time to explain, but it is better. Again, personally, to consider add as addition, right? But now the subtraction becomes the reverse of that vector. So for instance, if you have the vector v, and you have the vector u, to perform v minus u, it is more intuitive to think of u minus u as this green vector first. Now you start from u, the blue one, and you flip it to the other direction, which is minus u. And now we can add v and minus u together. And now adding is more intuitive. Oh yeah, we start at v and then we walk two steps in two different ways, and the result here is indeed v plus minus u, which is v minus u. And so that's how you deal with minus sign, and also the way you think about that vector. So that's a plus, that's a minus. There are a little bit more. Yeah, let's go over them. There are actually two other ways to perform something on vector. We are not going into details too much on this one because I don't have enough examples, and because it's just a basic that you might see anyway in the future. So if you have a vector, which is again just a line, like once you have a line in terms of physics point of view, remember that they think of a vector as a line that has a length and a direction. And what is the length of a vector? And here it is. And that's the notion of vector's length, which you can easily use the Pythagoras theorem, because if you have a plane, if this is a vector AB, this means you walk to the right by A steps, you walk up by B steps, and these two movements happen to be orthogonal. So you can find the length of this by using the Pythagoras theorem. A square is A square plus B square. So C is square root of A square plus B square, which is what we see in this formula. And on the left is a way to abbreviate. Because sometimes we care about the norm or the length, but we don't have to compute, or we don't want to compute. So when you discuss the norm or the length, then just put it right there. That's a norm for 2 dimension, of course. And just a side note here, this notation looks familiar. It looks as if it is an absolute value, doesn't it? And indeed, it's actually the same. Because if you think about it, the absolute value is actually the norm, right? You have a line, you have 0, this x vector. You don't care whether it points to the left or to the right. If you want to find the absolute value, then if you want to find the length, then that length can be computed using the absolute value. So yeah, in a sense, this norm notation they first they resemble the absolute value. Second, they do have the same meaning, which is the length. Okay, so that's how you compute a norm. And lastly, again, we don't need this in this class, but this is actually a important notation in vector, which is the dot product. So the dot product is a way to multiply vector. And because recall that we can multiply a vector by a scalar. This is a scalar, just a single number, like 3, 5, minus 2. But we did not mention that, you can actually multiply two vectors together. And yeah, we can do. And the thing is, we can do it in more than one way. And that's something confusing about a vector. Yeah, you can multiply vectors in way or another. And that's why this product has a name called a dot product. And just in case, another way is to do the cross product. Which actually require the vectors to be 3-dimensional. But yeah, anyway, there are more than one way to define products, and they mean different things. They are used in different aspects. For the dot product, again, this is in no way intuitive. So you multiply the first coordinate together. Maybe that works. You multiply the second coordinate together. Yeah, okay. But then you add them together. You might see on the right and see, wait, where is the vector notation? Is it gone? The answer is yes, it's gone. But the dot product is kind of weird in the sense that you have a vector, you perform a dot product, and the result is a number, which is weird. Well, maybe not that weird if you think about the norm, but it's the same thing, right? You have a vector, and the result is a number, but that number represents the length of a vector. But it doesn't represent anything immediately about these two vectors. Just a formula that is helpful in some way. And so yeah, I have just a short theorem. In case you are curious where you use it, we can use this dot product in this formula to compute the angle between two vectors. So if you have a vector u, and if you have a vector v, let's say we put the initial point at origin, so that there's an angle between them. We can actually compute the angle using the norm we just saw above and the dot product, which at this point it seems like it comes out of nowhere. But why would an angle be related to the product? But there's one application among thousands of applications of the dot product. Okay, yeah, that's the end of the introduction of what a vector is and what it means when you transform a vector, a single vector, on a plane. And there's an exercise, just a quick computational exercises. And I will see you in the next section.